Hello there and welcome back. In firmware development, there are times when you want your firmware to take actions based on time. At the very least, you might want to introduce some artificial delays. And one of the ways that we get this done is to use a busy loop, which is the use of a for loop just to keep the processor busy. And this is not a very smart way to go about it. So microcontroller units, and I mean all modern microcontroller units, include peripherals that are known as timers, which are essential for time-based generation. And in this video, I'm going to explain to you all the theory you need to understand about timers on STM32. So let's get started. Alright, so let's look at what a timer is and the components in a timer. A timer essentially is a free running counter. Okay, so I'm going to use a block diagram here. Let me select a pen and then I'm going to use a block diagram here. Let me choose a pen here. Okay, so I'm going to draw this block diagram here to represent roughly what's inside a timer. At the very least, every timer needs a clock source. Okay, so I'm going to draw the clock source here. Let's call that CLK. This clock source helps the counter in the timer to count either up or down. There are different modes of counting, but just to help you understand, I'm just going to work with counting up or counting down. And inside the timer, there is a register called the counter register. Let's indicate this with CNT. Okay, and then inside the same timer peripheral, there is another register which is known as the ARR, auto reload register, ARR. And then one other key component is a prescaler, and I'm going to explain what each one of them does. So let's call this a prescaler. Okay, now for a moment I just want you to ignore this diagram I have drawn to represent a timer, and then let's bring the knowledge home to something that is more realistic. Okay, so I'm going to move away from here and then I will let us come back to this drawing. Now imagine that as a human being we all do count, right? And when we are counting, we leave intervals between each instance of the count that we do. And so I'm going to draw something here. On the y-axis, I'm going to let us represent the current value that you are counting. Okay, so on the y-axis is the value that you are counting, and on your x-axis is time. Okay, so this is value and then this is time. Let's just imagine that you count and then you leave 1 second between each count that you do. If I want to take an action every 5 seconds, all I have to do is to use your counting as a timer, because as long as you can maintain a consistent period of pausing between each count, I can leverage that to serve as a counter for whatever action I want to take. So all you have to do is, I will say count to 5, right? So you start from 0, okay, and then you count to 1 here. So this is 1, so you count to 1 and then you pause for 1 second, and then you count to 2, you pause for 1 second, you count to 3, you pause for 1 second, you count to 4, you pause for 1 second, you count to 5, you pause for 1 second. Now once you count to 5, you fall back to counting from 1 again. Okay, so like you fall back to 0 again. Let me help this drawing here. You fall back to 0 again, and then you count 1, 2, 3, 4, right? 1, 2, 3, 4, and then this is the 5th one. Once you get to 5, you fall back once again. So you can see that in between every time when you started counting and you stopped counting, I should be able to get 5 seconds from there. Okay, and I should be able to trust and leverage this strategy to do counting. And this is a very loose description of how timers work in your microcontroller. It is a free counting device. Like I said, it can either count up, it can count down, or it can do a center aligned counting. It is not necessary now for the understanding, so I'm just going to use counting up. The approach you use or how you configure it to do the counting doesn't really matter in this particular case of the explanation, except the fact that because it's counting speed, okay, or the pauses between each successive count can be configured to be consistent, we can leverage that to do timing, to generate a time base in our firmware. And the reason why this approach is intelligent and a very nice one is it doesn't waste the processor's time. So you don't have to use a busy loop just to get your processor to introduce timing into your firmware. What's gonna happen is that once you count to the set period, okay, so let's say you want to count 5 times. So once you count 5 times, once it gets to the 5th count, it resets back to 0. Now when it is resetting back to 0, it can raise an interrupt. Okay, so it can raise an interrupt here, and then here also it can raise an interrupt. And so what it means is that the main processor can be busy doing other important things that are needed in the firmware, while this peripheral runs on its own, independent of the processor. And then once a particular time has elapsed that is important to the firmware, the timer is going to raise an interrupt. So we get an interrupt here. I'm going to use an I to indicate an interrupt, and then we get an interrupt also here. Okay, so this is how timers work at the very basic level. Once you understand this explanation that I have given you, it's gonna be very easy for you to work with timers. Now with this understanding, let's go back to the diagram that we started with. Okay, so let me clean the unintended. Yeah, so I stated that the timer is a peripheral and is a free counting peripheral. So free counting, it is essentially counting the same way I explained to you, and it is independent. Okay, independent of the processor. So what it means is that it will be doing its counting independent of whatever the processor is also doing, and by this the processor is free to attend to more important stuff. Now these 3 registers in here play a very important role, and like I mentioned, the timer needs a clock source. Okay, so what I have drawn here is a clock source, right? Now the way the timer works is that it can choose that on the rising edge of each clock pulse. Okay, so here, and then so here is rising, this is falling, and then here is rising. Okay, so it can decide that on every rising edge or on every falling edge, it is going to increment whatever value is in the count register by 1. Okay, and what that means is also that the count register has a resolution. For example, it could be a 16-bit, it could be a 16-bit timer, It could be a 32-bit timer. It could be a 12-bit timer. It depends on what the designers and the manufacturers decide to use. Now, the resolution of this count register plays a very important role on the limitations of the timer, because as you can imagine, if let's say it's a 16-bit counter, what it means is that it cannot count above a value that is bigger than the maximum unsigned 16-bit value we can store, which is I think 65,335 or something thereabout. So the resolution determines the maximum count, and because the period is also affected by the count, it also affects the period that you can use to decide on how often it should raise interrupts. I know that's a mouthful, so I'm going to take time to explain them one by one again. Now, we have established that the counter can decide on which edge of the clock signal it's going to increment what is in its counting register. Okay, now let's come to the prescaler before we talk about the ARR. The prescaler here helps you to control your timing. As you can imagine, if your clock source here is 100 megahertz and you want to use this to achieve a particular frequency of interrupt being raised, you need to be able to affect this frequency here. The faster the clock signal, the faster the count value in the count register increases over time. The slower the clock signal, the slower the value increases. So it's essentially going to be at a point the count is going to store 1 and then 0, and then on some edge, let's say on the rising edge, it goes to 1. On the next rising edge, it goes to 2. On the next rising edge, it goes to 3 until it overflows its bound, right? So you agree with me at this moment that the speed of the clock that is coming in is going to directly affect how fast the value in the count register increases. Okay, we have that agreement now. Now, because the clock signal is already configured, as you would remember from previous episode, we've learned how to use either the HSE or the HSI or the PLL to determine the clock speed at which your processor operates. So the only source of control for you when it comes to the speed at which your timer works is the prescaler here. Okay, so this also lets you decide on a value that is going to be used to scale down. So it's just the clock speed. Okay, so let's say the clock speed, I'm just writing CLK for clock speed, divided by whatever you store in your prescaler. This is going to be the actual frequency at which the timer is going to count. So let's call this timer CLK. Okay, so you use the prescaler. It could be 32-bit, 16-bit. You get all this information from the reference manual that you have to read, right? So you store a value in there that basically just divides the actual clock frequency in order to achieve the actual timer clock frequency. This is all to help you to be able to control the rate at which the counting here occurs. And remember, the rate at which the counting occurs directly affects the frequency at which you will raise interrupts, like you saw from this diagram here. Okay, so now let's talk about the ARR register. The ARR register stands for auto reload, and you use that to determine the period at which the interrupt, so let's say I1, I2, I3, ... Okay, so you use the ARR to set a value. So for example, at a point the count could be 0. So let's say the count register is storing 0. If I set in ARR is equal to, let's say, 10, okay, and let's imagine that I have chosen a particular prescaler. I'm just calling it X. I've chosen a particular prescaler that makes my timer clock run at 1 hertz. Okay, this is all fictitious. So let's say my timer clock, I'm going to write TIMCLK for timer clock. Let's say it's equal to 1 hertz. What it means is that every 1 second there is a rising edge or there is a falling edge. Now with this configuration here, what it means is that every 1 second my count is going to increase by 1. Okay, so on the first second my count will be 1, second is going to 2, 3. So ARR here is determining the period at which I want an interrupt to be raised. So the timer is going to keep counting until it reaches the value stored in the ARR register, and once that value is reached, this situation here is going to occur. It's going to raise an interrupt, and that is going to pause the processor from whatever it is doing, and then it has to execute the code you put in the interrupt service routine that reacts to such events from the timer peripheral. So assuming these fictitious values that I have put here is able to give me a pause of 1 second between each count, then it means if I store in ARR the value 10, then it means I'm going to get this interrupt raised every 10 seconds. This is the very basic thing you need to understand about the timers as far as the theory is concerned. Everything we've discussed here has a one-to-one mapping on the code that we will begin to write in the next episode. Before we end this video, let me tell you about the different kinds of timers that you find on the STM32. So there is the basic timer. Okay, so we have the basic timer. We have the general purpose. We have the general purpose. And then we also have the advanced timers. So advanced timers. Advanced timers. Okay. Now what are the difference? This is the most basic form of a timer. Its purpose is for time-based generation. So precisely what we've described, right? So time-based generation, just to generate time. All right, and then there is the general purpose. This one is advanced than the basic. It can have input and output channels, which are all things we'll talk about, input or output channels. So you can use the same timer peripheral to control the signals that are available on some particular GPIO pins, and in that case it means we can use it to do things like measuring. Okay, so we can do things like measuring the frequency of a signal. So we can measure frequency of an input signal. These are all things we talk about in practice. We can use it to also generate pulses or PWM. So if you want to control servo motors, you want to control the brightness of an LED, or you need a PWM signal for any of the purposes for which PWM is needed, then it is the function of a general purpose timer, which works together with either its input or output channels to help you do what you need to do. So it is usually called input capture or output compare mode. These are all things that we talk about. And then we also have the advanced timers. These ones have very peculiar applications. For example, some of them are needed for motor control, or digital power conversion applications. Applications. So just know about these different types of timers. Then the next question becomes, okay, what is the relationship between these different kinds of timers? In actual fact, on STM32, there are about 9 categories of timers. So the 3 I have shared with you are just the commonest categories that you will have to work with. And so don't take this as a complete knowledge. There are things that you can't do with the basic, the general purpose, or the advanced, and so you have to read more to be able to find out what the other categories can do. But these are the commonest, and so once you know how to work with them, you will be able to work with the others. And because we are using CubeHAL, the API or the libraries actually makes it consistent. Like how we work with these are very consistent. Okay, now I'm going to draw a diagram to explain the relationship between them. So what it means is that if this is a basic timer, it is contained in a general purpose timer. Okay, so general purpose. And then it is also contained in the advanced timer. So what this means is that the general purpose timer, this one, can do what this guy does. Okay, and then the advanced timer can also do what the general purpose timer does. The reason I'm sharing this knowledge with you is to help you write portable code, because you might write a firmware for a particular family or instance of the STM32 microcontrollers, and you might use a particular timer that might not be available on some other target. And so you need to know this knowledge to guide you when it comes to choosing. Essentially, don't go above the capabilities that you require in a timer. That is going to help you achieve portability. Now, the last thing I want to show you before I end this video is a document from ST Microelectronics that tells you the availability of timers in their microcontrollers. Okay, so I have already opened that document. Let me scroll up so you see the name. It is called AN4013, or you can just Google STM32 timer availability document. This document tries it best. The reason I'm saying tries it best is that sometimes it is outdated, but it tries to tell you all the different timers that are available in the different families and instances of the microcontroller unit. And the most important thing you want to look at here is a table. Okay, so you jump straight to simplified overview of timer availability in STM32FX products. If your microcontroller is an FX series, if it's an LX, then you go here. So just look at the kind of microcontroller you are using and then go to the table. I am using STM32F4, so I click on this because F4 is FX, right? Let's make space here. This is 100. Maybe let me make it a bit bigger. Hopefully it's legible for you. But the way you look at this table, or how you make sense of this table, is that there's a timer type here for this column, and it tells you whether it's an advanced timer, it's a general purpose timer. It also tells you the resolution. Remember, I mentioned that some could be 16-bit, some could be 32-bit, so it mentions that also. And then there's also the part that tells you which timers are basic timers. Okay, and then it can also tell you the number of channels and whatnot in the particular timers. So you want to look at the column that has the part number of your microcontroller unit. So I am using STM32 F4, so we look for F4. So this is STM32 F401. Mine is F407, but essentially if you look at them very well, it's always going to tell you. So this is STM32 F4 or F2, you see. So I fall in here. It says excluding F401, so it means I fall in here, my microcontroller fall in here. All right, so then I look at it and I say, okay, then it means I have timer 6, I have timer 7, which are basic. And see the good thing that ST have done when it comes to timing or timers is that they have made sure that if, let's say, you have timer 6 on your microcontroller unit and I also have timer 6 on my microcontroller unit, they are identical. So this helps make your code portable. Now, one confusion that I've seen people get is once they see, let's say, timer 14, they assume that it means there are 14 timers on their microcontroller. That is not true. The timer name here is just an identifier for a particular kind of timer. Okay, so you could have only 4 timers and one of them could be timer 6, timer 7, timer 13, timer 14. It doesn't mean you have 14 timers. It means that particular kind of a timer is available. So if you write code targeting timer 6, any microcontroller here that has timer 6 in there should be able to work perfectly without you having issues with portability. Thank you very much for watching this. If you haven't subscribed and you're watching this on YouTube, please do well to subscribe. And I will see you in the next episode where we write code to see how to configure everything we've learned about timers so far. See you.